Distillation is currently the most misunderstood word in AI, and it's about to cause a huge problem. There's a potential that the US government might ban open models coming out of China because there is a lot of confusion about what exactly distillation is. And it seems like a lot of people are getting it wrong. So I thought I'm going to create a video explaining what exactly it is and how it relates to what is happening right now. Okay, before that, we need to look at what exactly is happening. So last year in July, Moonshot released K2, which is their non-reasoning model. It scored 19 on the Artificial Intelligence Index. Earlier this year, they released K2.6, which scored 44. And now they released K3, which is their most capable model. And on the same benchmark, it's within 3 points of the most capable model on Earth, that is Fable 5, which sits at about 60%. Now, there is a lot of discussion that how Moonshot was able to train a really capable model in such short period of time and make it open source. Some people think this is because of distilling bigger frontier models from US companies. Now, I'm not going to go into the geopolitics, but let me explain where they get this wrong. Okay, so for this, we actually need to understand what distillation is and why companies do that. So most of the models that we see today, even through APIs, they are usually distilled from a much larger model, which is a lot more capable, but it's prohibitively expensive for these companies to serve for inference. So the idea is that they train a smaller model which compresses the capabilities of a teacher model. And this smaller student model is what we as users actually see. But how exactly do they do this? Well, this is where this paper, Distilling the Knowledge in a Neural Network from Jeff Dean, Jeffrey Hinton, and Oriel comes into play. Now, they have in the abstract, it is possible to compress the knowledge in an ensemble into a single model, which is much easier to deploy. And that is kind of the whole idea of why you want to have capability distillation into a smaller model. But the question is, how exactly do you train that small student model from a bigger teacher model? Now, in order to understand this, we need to look at image classification. So if you look at this number 2 and you want to classify it or identify it as using a neural network, we need hard labels to tell the model that this is number 2. So we're going to set the label at 2 equal to 1, and the rest is going to be 0. This is called one-hot encoding. Now, the way we train bigger teacher models is that they are going to learn the representation. They assign probabilities to different classes. Say in this case, the number 2 gets assigned 90% probability, but there are going to be non-zero probabilities assigned to other classes as well. These are called soft labels, which basically shows you the full spread of a probability distribution across all the classes. And the most interesting thing here is these wrong probabilities that are assigned to wrong classes. Now, in this dummy example, 7 has higher probability compared to 3. And the reason is that this 2 has a flat top like 7. Now, Hinton called this dark knowledge because these wrong answers actually keep greater insight into generalization rather than learning hard labels. However, the resultant probabilities are so small that you can't really train a model on it to learn the generalization. So what Hinton observed was that if you divide these logits coming out of the model by a parameter called temperature, you can actually adjust the temperature so that you can flatten out the distribution. And now it becomes a relative score among the probabilities rather than the absolute number. Then you can train a student model on exactly the same data, but now you want the student model to replicate the probability distribution coming out of the teacher model. And if the student model is able to learn this whole probability distribution, that is going to enable it to transfer capabilities. And this is the text textbook definition of distillation. So you actually need access to logits in order for the student model to learn from the teacher model. Distillation depends on data. This is where we need to talk about today's sponsor. So if you're building something that needs search data behind it, say an SEO tool, a reporting dashboard, or some kind of automation or an agent, today's sponsor, Data for SEO, can be that data layer for you. They are one of the top SEO data providers, and their API covers a lot of ground. They also provide marketing data around it that can be connected to a number of different agents. The best part, you don't have to commit to monthly plans before you even know how much data you're going to need. It's pay as you go. So your cost scales together with your product and your customers. And the pricing works for smaller projects too, and the support is available around the clock. And they will actually help you implement the APIs and work through the technical stuff with you. Link is going to be in the description. Register for a free account. You get $5 in free credits to start testing your own use case. Now back to the video. Okay, so this was image classification. What about large language models? So in large language models, these are next token predictors. However, the way they predict next token is that they are going to make prediction for every possible token in the vocabulary if it tries to determine what is the next token in the sequence. So it basically converts into a multi-class classification problem, exactly the way we saw it with the image classification problem. And again, we're going to take the logits and log probabilities of every possible token in the whole vocabulary, and then you can use the same in order to train a student model. However, if you're using an API, this is going to only give you access to the most probable token. Say if you're using ChatGPT or Gemini in the world, and even if you're using the API, you get only the most probable token. They don't really expose the whole probability distribution. And that is the signal that you actually need in order to train a subsequent model from this bigger teacher model, which is not present through the API. There are ways around it, which we're going to look at in a minute, but distillation is a really common practice in frontier labs. They usually train bigger capable models and then distill smaller models from those. However, the parameter count actually matters. You can't really distill the capability from a huge multi-trillion parameter model into, say, a few billion parameter model. You actually need intermediate steps. So you will probably have a big model that is distilled into a medium model, and then a medium model distilled into a smaller model. Now today, most of the time is spent on RL, and we have some open example of these. So if you look at DeepSeek R1, they actually distilled R1 into much smaller models. Okay, now going beyond the classic textbook definition of distillation, you can divide it into 4 different types, and each one of them needs different type of access to the model. The first 3 needs access to either the weights of the model or the log probabilities. These include logit knowledge distillation feature, which enables to learn from the model if you have access to the internal activations of the weights, and then on policy knowledge distillation, where a teacher creates to students tokens. We're going to look at that in a minute, but there is 4th, sequence level distillation. Now for this specific case, you don't need access to the model weights or log probabilities. You can actually take the sequence sample data from the teacher model in order to learn from it. However, what you learn from it is very limited. Now, if you look at proprietary APIs like Anthropic's API, they don't expose log probabilities. They give you simply the sequence coming out. They also make it harder to learn from the chain of thought because they give you summarized chain of thought rather than the raw chain of thought. So the only way you can do anything from a proprietary API is to use the sequence level knowledge distillation. Okay, so we need to look at much deeperly. Now, this is not a new approach. It goes back to 2016 in a paper by Kim and Resh sequence level knowledge distillation. It's actually a really simple idea. They say that if you can't see teacher's distribution, you'd sample a huge pile of its finished output and fine-tune your model on those. It's a very similar approach to supervised fine-tuning, just like the ordinary training data that you would use. So at an industrial scale, here is what it would look like. You're going to take a fleet of accounts and proxies at a frontier model, point at them. Then you're going to what you are interested in. Then you filter out and deduplicate the outputs. And whatever is left is basically the data that you're going to be using for supervised training, which essentially is what we would call output harvesting. In a lot of discussion that you see in news about distillation is specifically output harvesting. Now, some of the American frontier labs have pointed out that they see this at industrial scale. So for example, there was a report from Anthropic back in February that they saw about 16 million exchanges with Claude through approximately 24,000 fraudulent accounts coming out of China. Now, people have been doing this sequence level distillation for a while now. We can go earlier to Alpaca and Vicuna. Those were the earlier data created using the outputs from OpenAI APIs. So this is a well-known technique. However, this is mostly a violation of terms of services rather than a large-scale distillation, because this is not going to give you capability transfer. This is mostly imitation, which it basically copies the style but not the capability of the model from which you're getting this data. Okay, so if something like this cannot give you capability, where exactly does the capability actually come from? And for this, we need to talk about the training pipeline as a whole. Now, here is what a modern training pipeline looks for a large language model. You have pre-train, mid-train, SFT, and RL. Now, pre-training and mid-training basically defines the base capabilities. And this is where companies spend the most time, even today. And you lock the data for this months before launch. Now, pre-training is extremely expensive. It happens once in a while. And usually companies use the same pre-trained model for further post-training. That is going to result in different versions of the model. Now, mid-training is the interesting part here, because you can use this to distill over a targeted corpus like math or code to basically inject that one specific skill that you are interested in an already pre-trained model, but do it much more cheaply. Now, supervised fine-tuning essentially controls the style and behavior of the model, but then comes the large-scale reinforcement learning, where model practices tasks and get trained on attempts that actually works. So a lot of effort right now is being focused on RL and RL environments. And this plays a critical role. There is a specific type of distillation called on-policy distillation. And there are some really interesting papers on this. Link to some of them are going to be in the video description. Now, in this case, the student actually writes its answers. Then the teacher creates every single token of that answer using its log probabilities. Now, the beauty of this approach is that the student gets corrected on its own mistakes. And the teacher essentially at this stage is a judge, which essentially is a reward model that scores students' answers. This is sometimes called reinforcement learning through AI feedback. And this actually works surprisingly well. So there was a study in which they showed that you can push AMY 2024 score to 4% using on-policy distillation compared to off-policy distillation. But the beauty is that you don't need that much compute. They use about 1800 GPU hours compared to almost 18,000 GPU hours for simple RL. We're talking about an order of magnitude more. But the problem is that you still need access to teacher's log probabilities, which are not available through simple APIs. Now, there is an argument that you could potentially do imitation learning, but that is not going to be possible at this scale. A final RL run usually involves tens of millions of rollouts. A rollout in this case is essentially a completed task. Now, according to Nathan Lambert, you will probably need 20 to 40 million rollouts for this to work, which is essentially impossible at paid APIs, especially if you're accessing something like Fable 5 level models. Okay, so that was distillation in a nutshell. Now let's look at some reports about the feasibility of distilling Fable 5 into Kimi K3. And I think it's important to look at the timelines. So Fable 5 was released on June 9th, but then Anthropic had to take it down because US export controls on June 12th, so we had access to it for only 3 days. Then it was widely available on July 1st. K3 was released on July 16th. So unless Moonshot had access to the model by hacking into Anthropic's own server, it was available for only 18 days through the API, assuming they didn't have access to it through the project Glasswing. Now, with this timeline in mind, given that it's a 2.8 trillion parameter model, 3's pre-training and mid-training data should have been locked months earlier. But let's say even if they had access to it through some sort of API, that would only transfer the style, not the capability, unless they had access to log probabilities. Now, geopolitics aside, I hope this video gives you a good idea of what exactly distillation is, how it's done at scale, and what exactly do you need for it to actually work. Now, I hope you found this video useful. Thanks for watching, and as always, see you in the next one.